Welcome back to Chapter 3 of Principles of Mathematical Analysis. In this section, we develop two of the most practical tools for deciding whether a series converges, the root test and the ratio test. Up to now, our main weapon has been the comparison test, but that always required us to already have a known series to compare against. The root and ratio tests are different. They look only at the terms of the series itself, and they reach a verdict by quietly comparing the series against a geometric series. We will state both tests, prove them, work through revealing examples, and finally see a theorem that explains exactly how the two tests are related. Let's begin. Here is our roadmap. We start with some motivation, recalling why we want tests that depend only on the terms of the series. Then we state and prove the root test, followed by the ratio test. After that, we look at examples that show the two tests in action, along with remarks comparing them. We then prove a theorem that makes the comparison precise. Finally, we summarize the key takeaways. Let's recall where we stand. The comparison test is powerful, but it has a practical drawback. To use it, we must already have a second series whose behavior we know, and we must verify a term-by-term inequality against it. In other words, the comparison test does not work in isolation. It always needs an outside reference series, supplied by us. Next, let's see what we would prefer instead. What we really want is a test that is intrinsic. That means a test we can apply by looking only at the terms a sub econ n of the series in front of us, without having to hunt for a clever comparison series. We feed in the terms, run a computation, and get an answer. Next, let's see what computation does the job. Here is the key idea behind both tests. They each compare the series, behind the scenes, against a geometric series. The root test measures how the n-th root of the size of a sub he n behaves. The ratio test measures how consecutive terms compare in size. In both cases, if the relevant quantity stays safely below 1, the terms shrink at least as fast as a convergent geometric series. Next, let's recall why the geometric series is such a reliable benchmark. Before stating the tests, let's recall our benchmark. The geometric series, the sum of x to the n, converges exactly when the absolute value of x is less than 1. This single fact is the engine behind everything in this section. The key idea is shown in the picture. The smooth red curve is the decaying geometric term, beta, to the n, with beta less than 1. The blue dots are the sizes of our series terms, the absolute values of a sub n. As long as the blue dots eventually stay below the red curve, our terms are dominated by a convergent geometric series, and the comparison test hands us convergence. Both the root test and the ratio test work by establishing exactly this domination. Keep this picture in mind as we state the root test. Now the root test. We are given an arbitrary series, the sum of a sub n. We form a single number, alpha, defined as the upper limit, as n goes to infinity, of the nth root of the absolute value of a sub n. Taking the absolute value first means the test applies to series with terms of any sign, even complex terms. Taking the upper limit means alpha always exists, possibly as plus infinity. This one number, alpha, will decide the fate of the series. Next, let's see the three cases. Here are the three cases. If alpha is less than 1, the series converges. If alpha is greater than 1, the series diverges. And if alpha equals exactly 1, the test gives no information at all. The series might converge or might diverge, and we must use other methods. So the root test is decisive whenever alpha avoids the single boundary value 1. Let's picture these three regions on a number line. This number line summarizes the root test. The value of alpha sits somewhere on this axis, in the green region to the left of 1, where alpha is less than 1. The series converges. In the red region to the right of 1, where alpha is greater than 1, the series diverges. Exactly at the point 1, shown in gray, the test is silent. The whole proof comes down to understanding why the dividing line falls precisely at 1, and the reason is the geometric series. Let's prove it. Before the details, here is the plan. There are 3 cases matching the 3 conclusions. For alpha less than 1, we trap every term from some point on below beta to the n for a fixed beta between alpha and 1, then finish with the comparison test. For alpha greater than 1, we produce infinitely many terms of absolute value bigger than 1, which means the terms cannot tend to 0, so the series diverges. For alpha equal to 1, we simply display 2 example series, one convergent and one divergent, both having alpha equal to 1. Let's carry out the first case. We begin with alpha less than 1. Since alpha is strictly below 1, there is room to slip a number beta strictly between alpha and 1. Now recall theorem 3.17. Part B. The upper limit alpha has the property that only finitely many terms of a sequence can exceed any number bigger than alpha. Since beta is bigger than alpha, this means that beyond some index n, every nth root of the absolute value of a sub n is less than beta. Next, we turn this root inequality into a bound on the terms themselves. Raising both sides of that inequality to the nth power removes the root and gives a clean statement. For every n, at least n, the absolute value of a sub n is less than beta to the n, but beta lies strictly between 0 and 1. So the geometric series of beta to the n converges. The comparison test now finishes the job. Our series is dominated, term by term, from index n onward by a convergent geometric series, so it converges absolutely. The first case is complete. Next, the divergent case. Now suppose alpha is greater than 1. By theorem 3.17, the upper limit is actually attained along some subsequence. There is a subsequence of indices along which the nth root of the absolute value of a sub n converges to alpha. Since alpha exceeds 1, that root exceeds 1 for all large members of the subsequence, which forces the absolute value of a sub n itself to exceed 1 for infinitely many n. But then the terms cannot possibly tend to 0. Recall theorem 3.23. If a series converges, its terms must tend to 0. Since that necessary condition fails, the series diverges. Next, the borderline case. Finally, the borderline. Consider 2 familiar series, the harmonic series, the sum of 1 over n, which diverges, and the sum of 1 over n squared, which converges. Why is alpha equal to 1 for both? Because the nth root of n tends to 1, a standard limit we established earlier, and therefore the nth root of 1 over n and of 1 over n squared also tend to 1. So alpha equals 1 in each case. Here we have 2 series with the very same value of alpha, yet opposite behavior. This proves that when alpha equals 1, the root test simply cannot decide the question. That completes the proof of the root test. Now let's turn to its close relative, the ratio test. The ratio test looks at consecutive terms instead of roots. Here is the convergence half. The series converges if the upper limit, as n goes to infinity, of the absolute value of the ratio of consecutive terms is strictly less than 1. Intuitively, if each term is eventually a definite fraction smaller than the one before it, the terms shrink geometrically, just like a geometric series, and so the series converges. Notice we use the upper limit here. The ratios are allowed to dip and rise, as long as they do not creep up to 1 in the long run. Next, the divergence half. And here is the divergence half. The series diverges if the absolute value of the ratio is at least 1 for every n, beyond some fixed index n sub 0. Note the asymmetry with the convergence half. For convergence, we use the upper limit being below 1. For divergence, we demand that every ratio from some point on is at least 1. This is a stronger requirement than just a lower limit being at least 1, and the proof will show why we phrase it this way. Next, an important warning. A warning exactly parallel to the root test. If the limit of the ratio equals 1, the ratio test tells us nothing. The same two series make the point. For both the harmonic series and the sum of 1 over n squared, the ratio of consecutive terms tends to 1, yet one diverges and the other converges. So a ratio limit of 1 is genuinely inconclusive. Next, let's prove the ratio test. Suppose the upper limit of the ratio is below 1. Then we can choose a number, beta, still below 1 but above that upper limit, and an index n, so that every ratio past n is less than beta. Now we cascade. The term at n plus 1 is less than beta, times the term at n. The term at n plus 2 is less than beta times that, hence less than beta, squared times the term at n. Continuing this telescoping pattern, the term at n plus p is less than beta to the p, times the absolute value of the term at n. Next, we rewrite this as a single clean bound. Setting Hessian equal to n plus p, the cascade collapses into a single inequality. For every n greater than n, the absolute value of a sub n is less than a fixed constant, namely the absolute value of a sub n times beta to the minus n multiplied by beta to the n. The crucial point is that the constant does not depend on n. Only the beta to the n factor changes. So the terms are dominated by a constant multiple of the geometric series of beta to the n, which converges because beta is below 1. The comparison test gives convergence. The first case is done. Next, divergence. For divergence, suppose that from some index n sub 0 on, each term is at least as large in absolute value as the one before it. Then the sizes of the terms never decrease from that point on. A sequence whose terms never shrink in size cannot tend to 0 unless they were already 0, which would make the ratio undefined. But recall the necessary condition for convergence from Theorem 3.23. The terms of any convergent series must tend to 0. That condition fails here, so the series diverges. Notice how crude this is. We never even looked at how big the ratio is, only that it stays at least 1. That completes the proof of the ratio test. Next, some examples that reveal a real difference between the two tests. Here is a revealing example. The series interleaves two geometric series, the powers of 1/2 and the powers of 1/3, taken in the order 1/2, 1/3, 1/2 squared, 1/3 squared, and so on. Each individual piece is a perfectly nice convergent geometric series, but by shuffling them together, we create a series whose consecutive ratios behave wildly. Let's compute the relevant quantities and see what each test says. Look at the 4 numbers. The ratios swing all the way from a lower limit of 0 up to an upper limit of plus infinity, because going from a 1/3 term to the next 1/2 term, the ratio blows up. So the ratio test is helpless here. Its upper limit is infinite, well above 1. The roots, however, are tame. The nth roots stay between 1 over root 3 and 1 over root 2. The root test uses the upper limit, 1 over root 2, which is less than 1. So the root test cleanly concludes convergence. The root test succeeds exactly where the ratio test fails. Next, a second example with the same lesson. The second example tells the same story in a slightly different way. Here the powers of 1/2 are listed 2 at a time, with each pair in swapped order. So a smaller term is always followed by a larger one. The lower limit of the ratios is 1/8, and the upper limit is 2. Since the upper limit, 2, is bigger than 1, the ratio test once again gives no conclusion. But the nth roots actually converge to 1/2. Since 1/2 is below 1, the root test again concludes convergence. 2 examples, 1 moral. The root test can decide cases the ratio test cannot. Let's make that observation precise. Remark 3.36 weighs the 2 tests against each other. In day-to-day practice, the ratio test is frequently easier to apply, simply because computing a ratio of consecutive terms is usually less work than computing an nth root, and then its limit. So for many standard series, the ratio test is the convenient first choice. But ease of use is not the whole story. Next, the deeper comparison. The root test, on the other hand, has wider scope. Whenever the ratio test proves convergence, the root test proves it too. And whenever the root test fails to decide, the ratio test also fails. So the root test is strictly more powerful, never weaker. Our 2 examples illustrated exactly this. We will prove this relationship in a moment. One more remark. Neither test is subtle when it comes to divergence. Both detect divergence only in the crude way, by noticing that the terms fail to tend to 0. Next, the theorem that justifies the comparison. Here is the theorem behind the remark. For any sequence of positive numbers AC sub n, 2 inequalities hold. The lower limit of the ratios is at most the lower limit of the nth roots, and the upper limit of the nth roots is at most the upper limit of the ratios. In words, the root quantities are always squeezed between the ratio quantities. Let's see this as a picture before proving it. This picture shows the squeeze. On the number line, the 2 ratio quantities, the lower limit and the upper limit of the ratios, sit on the outside, drawn in red. The 2 root quantities, the lower and upper limits of the nth roots, sit on the inside, drawn in green. The interval determined by the root test is always contained inside the interval determined by the ratio test. This is exactly why the root test has wider scope. Its decisive interval is narrower and better placed. Now let's prove the second inequality. We prove the second inequality. The first is entirely similar. Let alpha denote the upper limit of the ratios. If alpha is plus infinity, the inequality holds automatically, since nothing can exceed infinity, and there is nothing to prove. So assume alpha is finite, and choose any number beta larger than alpha. By the meaning of the upper limit, only finitely many ratios can exceed beta, so there is an index n, beyond which every ratio is at most beta. Next, we cascade these inequalities, just as in the ratio test proof. Past the index n, each term is at most beta times the previous term. Writing this out for k running from 0 up to p minus 1, we get a chain of inequalities. Multiplying all of them together, the intermediate terms cancel in pairs, and we are left with the term at n plus p is at most beta to the p times the term at n. Setting n equal to n plus p, this says c sub n is at most the constant c sub n times beta to the minus n, multiplied by beta to the n, valid for every n, at least n. Next, we extract the nth root. Now take the nth root of both sides. The right side becomes the nth root of the constant times beta. As n grows, the nth root of any fixed positive constant tends to 1. Therefore, passing to the upper limit and using theorem 320, part b, we obtain inequality 18. The upper limit of the nth roots is at most beta, but beta was an arbitrary number greater than alpha. Since the inequality holds for every such beta, it must also hold for alpha itself, giving the upper limit of the nth roots is at most alpha. That is exactly the second inequality, and the proof is complete. Let's summarize. Let's gather the key points. First, the root test. Form the upper limit of the n root of the absolute value of a sub n, and call it alpha. If alpha is below 1, the series converges. If above 1, it diverges. And if exactly 1, the test is inconclusive. Next, the ratio test. Second, the ratio test. The series converges if the upper limit of the absolute ratio of consecutive terms is below 1, and diverges if that ratio stays at least 1 from some point on. The ratio test is usually easier to compute. Both tests work by secretly comparing the series to a geometric series. Next, the relationship between them. Third, theorem 3.37 tells us the root quantities are always squeezed between the ratio quantities. The practical consequence is that the root test has wider scope. Anything the ratio test settles, the root test settles too, but not the other way around. Coming up next, we apply these ideas to power series, where the root test will pin down the radius of convergence, the interval on which a power series defines a function. See you in the next section.